What was really discovered in the solar system in 2025? Dear traveler, greetings. Today, we are setting out to explore the mysteries of our very own solar system. Not a distant exoplanet, nor a star lost in the galactic night, but what lies close to home. For in 2025, new discoveries have shaken our certainties. Icy moons that might harbor underground oceans. Planets we thought were sterile, but perhaps still whisper traces of active chemistry. Asteroids carrying essential ingredients for life, and strange signals from areas we thought inert. And what if our solar system had far from revealed all its secrets? But before embarking on a new adventure, don't forget to like the video and subscribe to the channel so you don't miss anything. Thank you, and have a nice trip. The Sun, a vast incandescent sphere, reigns at the center of our solar system. It formed about 4.6 billion years ago from a cloud of particles that, under the effect of gravity, gave birth to a star. The matter concentrated into a core where enormous pressure and heat triggered nuclear fusion. This reaction releases the energy that lights and warms our planet. Without this natural engine, life would never have emerged. But beyond its vital role, the Sun influences many phenomena in space, from radiation to magnetic interactions between planets. This narrative explores the modern tools that reveal the dynamics of the Sun, its variations, and the effect of its cycles, while simplifying complex concepts. To unravel its mysteries, one must understand what solar wind is. This continuous flow of charged particles and electromagnetic fields comes from the corona, the outer layer of the solar atmosphere. Strangely, this corona reaches temperatures of 1,000,000 degrees Celsius, about 1.8 million degrees Fahrenheit, while the visible surface, the photosphere, remains much cooler. This anomaly has long puzzled researchers. To address it, NASA launched the Parker Solar Probe mission, which aims to study this atmosphere by approaching the Sun as closely as possible. On March 25, 2025, Parker Solar Probe will make a record approach after several flybys near Venus, intended to slow its course. It will approach just 6.8 solar radii from the heart of our star, or less than 5 million kilometers, about 3 million miles. At this distance, it will reach a speed of nearly 700,000 kilometers, about 435,000 miles per hour, a speed such that it could circle the Earth several times in an hour. To withstand the extreme heat, the probe carries a multi-layer thermal shield, designed to keep its instruments at a constant temperature despite the intensity of sunlight. Thanks to this proximity, the probe will collect data directly from the solar environment. The speed, density, composition of particles, and local magnetic fields will be measured precisely. This data will help understand the origin of the solar wind and its propagation through interplanetary space. Why do some areas produce a fast wind, others a slower one? How do the violent gusts that threaten our satellites or electrical grids arise? These questions are fundamental to better protect our infrastructure and refine our understanding of space weather. Meanwhile, another mission, Solar Orbiter, developed by Europe, complements this exploration. Launched in 2020, it maps the solar magnetic field and photographs the poles, invisible from the ecliptic plane. By rising above this plane through several flybys of Venus and Earth, Solar Orbiter offers us an unprecedented view of the Sun's high latitudes. It has already mapped the magnetic fields beyond 60 degrees of latitude, a major advance as these areas were previously unknown. It has also revealed the presence of coronal plumes, large structures of ionized gas rising into space. Unlike more fleeting phenomena, these formations seem to last over time. Powered by the magnetic bubbling of the solar surface, they might contribute to accelerating some particles of the solar wind. What was suspected now becomes observable. The Sun follows an 11-year cycle, marked by the gradual appearance and disappearance of dark spots visible on its surface. These areas, where the magnetic field is particularly intense, locally disrupt the temperature. The number and distribution of these spots reflect the overall activity of the star. High activity leads to more ejections and disturbances. In contrast, during a minimum, phenomena are rarer and less violent. We are currently in solar cycle number 25, which began at the end of 2019. Forecasts indicate a peak in activity by the end of 2025. At that time, the number of sunspots could approach 160. This data, far from being abstract, helps researchers anticipate changes in the solar wind. Increased activity raises the risk of geomagnetic storms that can affect our planet, as well as those with a magnetosphere. These magnetospheres act as a protective shield. On Earth, they deflect the most energetic particles, protecting the atmosphere and life forms. On Jupiter, they are even more powerful, creating auroras visible even from space. When the Sun enters an active phase, these phenomena intensify. This is what we call space weather, a set of invisible conditions with very concrete effects on planetary environments. Observing the Sun allows us to better understand our main source of energy, but also to prevent risks associated with its outbursts. This star, familiar though it may be, remains unpredictable. The Parker and Solar Orbiter missions thus have a dual objective: to enrich our knowledge and to enhance our vigilance. They unveil the complexity of a star we thought we knew. When the current cycle reaches its peak, spectacular auroras could appear much further south than usual. It will be necessary to anticipate the effects of possible storms, which could disrupt navigation, communications, or the power supply. Data from probes and telescopes will feed our models, refine forecasts, and perhaps one day allow us to predict these events as we anticipate terrestrial weather. The research is just beginning. Each close flyby of Parker, each magnetic map drawn by Solar Orbiter, each series of spots recorded contributes to enriching our image of the Sun. A more precise portrait of a star constantly in motion. A star that, while illuminating our days, remains a mystery. This observation work will continue, and the discoveries that result will continue to fascinate. Even after a century of study, we still discover unknown structures and extreme speeds, just a few million kilometers or a few million miles from the surface. The models adjust, the predictions refine. The peak of activity in 2025 will be a test for our tools, for our understanding, and for our ability to anticipate the fury of an omnipresent star. By cross-referencing Parker data, Solar Orbiter analyses, and cycle monitoring, we advance towards a global vision of what it means to live near an unstable star. From the boiling core to the corona, constant energy unfolds. It shapes space, influences our atmosphere, governs our environment. And every discovery reminds us of this. The Sun is not just a light in the sky. It is the beating heart of our system. A heart whose study remains one of the great scientific challenges of our time. Mercury, often perceived as the hottest planet in the solar system, remains an inexhaustible source of mysteries. In orbit closest to the Sun, it undergoes extreme temperature variations, up to 430 degrees or 806 degrees Celsius on its sunlit side, and nearly minus 180 degrees or minus 292 degrees Celsius in the dark. Despite this hostile climate, it maintains a global magnetic field, which is surprising given its small size. Today, researchers are preparing for a major rendezvous scheduled for December 5, 2024, the third flyby of the Bepi-Colombo probe. This joint mission by Europe and Japan promises to unveil unexplored details about the planet closest to our star. To assess the significance of this flyby, it is essential to recall the fundamental characteristics of Mercury. Its proximity to the Sun constantly exposes it to an intense flux of particles, which affects its thin gaseous envelope, called the exosphere. This layer, much thinner than a true atmosphere, continuously evolves under the influence of solar wind and interplanetary dust impacts. Furthermore, Mercury rotates very slowly on its axis. A day lasts longer than a year, accentuating the thermal contrasts. It is in this context that Bepi-Colombo's third pass will allow examination of the influence of these phenomena on the crust and the exosphere with unprecedented accuracy. Bepi-Colombo consists of two orbiters. One studies Mercury's surface and chemistry, while the other focuses on its magnetic environment. From its first flybys, the probe has collected data on the terrain, rock composition, and magnetic fields. The flyby on December 5th will mark a decisive stage. It is expected to refine our understanding of certain localized magnetic fields on the surface, where magnetism shows strong anomalies. An instrument dedicated to this study, equipped with highly sensitive sensors, will help retrace the planet's geological history by identifying areas that have retained traces of a past magnetic field. Scientists seek to better understand this magnetic memory preserved in the rocks. According to several research teams, the study of these local fields could reveal the age of certain regions. If some areas still retain residual magnetism, they must have solidified at a time when Mercury's field was more intense or functioned differently. Understanding this local magnetic distribution helps reconstruct the planet's thermal evolution and also sheds light on the formation of small rocky planets in the solar system. This third flyby will also focus on a striking anomaly, the unusual presence of sulfur in the exosphere. This outer gas layer easily escapes into space. Several processes can inject particles into it: solar wind, micrometeorite impacts, or surface heating. In Mercury's case, the high concentration of sulfur is intriguing. Researchers want to understand how this element manages to migrate to the exosphere. The instruments on board should help determine whether it comes from the rocks, the upper mantle, or surface reactions caused by the space environment. Beyond this chemical enigma, Mercury also fascinates with its global magnetic field, called the dipole field. Unlike Earth, Mercury is much smaller and should, in theory, have a completely frozen core. Yet, the presence of a magnetic field, even weak, suggests a metallic core still partially active. A core driven by an internal dynamo effect, despite seemingly unfavorable conditions. A new hypothesis, which scientists plan to test in 2025, proposes an unusual composition of the core. It could be rich in silicon, an element that, combined with iron, would alter the internal temperature and allow a thin metallic layer to remain liquid. This even reduced thin envelope would be enough to generate an electrical current maintained by the planet's slow rotation and internal thermal exchanges. This hypothesis is essential for rethinking planet formation. If a partially liquid core can persist in such a small planet, similar processes could exist elsewhere, even on distant worlds. Confirming or refuting the presence of silicon in Mercury's core will also influence our understanding of its composition and the collisions it has endured over time. Among the recently observed phenomena, another draws attention: the existence of twilight sodium geysers. Sodium, present on Mercury's surface, is released when micrometeorite impacts hit the crust at high speed. At sunrise or sunset, these atoms form a luminous plume that briefly rises into the exosphere like an ephemeral steam jet. These geysers have been captured by an onboard spectrometer analyzing X-rays. When a micrometeorite impacts the surface, it ejects fragments, releasing sodium. At dawn and dusk, the grazing light reveals these momentary plumes, which are invisible from Earth but detectable thanks to Bepi-Colombo's sensors, sensitive to X-rays and ultraviolet radiation. This discovery provides valuable information on the dynamics of the exosphere. The more micrometeorites there are, the more sodium is ejected into space, continuously feeding this thin envelope. Observing these geysers at different times helps to better understand the spraying of minerals and the effect of the space environment on a planet without a thick atmosphere. Mercury is constantly evolving under the influence of external factors. Unlike Earth, it has neither climate nor active tectonics. Its landscape changes under the regular impact of micrometeorites. Its position close to the Sun exposes it to intense and rapid bombardment. The spallation of the surface then becomes the main driver of its geological transformation. The study of the geysers also contributes to a better understanding of surface chemistry. Sodium becomes an indicator of soil composition and its erosion. By analyzing the proportions of various elements in the exosphere, researchers gain direct insight into the composition and alteration of the regolith, this layer of dust that covers Mercury. These studies illustrate the precision of the instruments aboard Bepi-Colombo. Each pass refines the readings and prepares for continuous observation that will begin when the probe enters orbit around Mercury. This will be the time to explore, without interruption, the residual magnetic fields, the structure of the core, and the chemical dynamics of the surface. As December 5, 2024, approaches, scientists' enthusiasm grows. The probe, already en route, is preparing to fly over this unique planet once more, to reveal new secrets. By cross-referencing data from the different instruments, researchers hope to better understand the origin of sulfur, magnetic variations, and the fleeting activity of sodium geysers. The following year, modeling will be refined in light of these measurements. The results will help determine whether a partially liquid core can generate a stable field despite the planet's small size. They could also reveal unknown elements, opening new perspectives on rocky worlds. Mercury is not just a scorching world. It is a complex magnetic planet, peppered with anomalies, each discovery bringing us closer to a better understanding of the solar system. The flyby of Bepi-Colombo will mark a new step forward in this quest, revealing clues about the internal structure, surface chemistry, and constant exchanges between the planet and space. This journey around Mercury is guided by our thirst for knowledge. By studying its magnetic fields and thin exosphere, we advance our understanding of rocky planets. This research will help to better define the conditions necessary to sustain a magnetic field in bodies otherwise considered too small or too close to the Sun. The flyby of Bepi-Colombo will therefore be much more than just a passage. It will be a decisive moment in the exploration of a world once thought to be simple, but which reveals itself, observation after observation, to be surprisingly rich. For centuries, Venus has fascinated astronomers and sky dreamers. Its brilliance in the night, enhanced by its cloud layer, makes it one of the most visible stars. This luminosity earned it the name Evening Star. Yet, behind this facade lies a hostile world, where the surface temperature is around 460 degrees Celsius, or 860 degrees Fahrenheit. This documentary invites you to discover recent breakthroughs on this burning planet and future explorations aimed at better understanding it. Recent observations made between 2024 and 2025 have confirmed the presence of phosphine in the clouds of Venus. Detected at a rate of 1 particle per billion, this molecule could signal unexpected chemical or biological activity. On our planet, phosphine can result from industrial processes or the activity of bacteria living without oxygen. This discovery has thus rekindled questions about the possibility that one day, or perhaps already, life may have found refuge in the upper atmosphere of Venus. In the same cloudy region, the presence of ammonia, detected at less than 100 particles per trillion, has sparked keen interest. This element is rarely stable in an environment as extreme as that of Venus, dominated by a crushing atmosphere and clouds laden with sulfuric acid. Its presence could indicate unprecedented chemical reactions or, according to some, the activity of microscopic organisms capable of withstanding these conditions. To test these hypotheses, experiments were conducted in the laboratory. Researchers simulated the Venusian atmosphere by introducing sulfuric acid, diluted to 20%. In this corrosive environment, they observed the behavior of amino acids. Some remained stable for more than 30 hours, showing that it is possible to survive, at least temporarily, in an environment as acidic as the clouds of Venus. These results paved the way for a fascinating hypothesis, that of airborne microorganisms. Unlike terrestrial life forms, these could have a protective envelope composed of solid proteins. This layer would provide a barrier against the corrosion of sulfuric acid and allow them to exploit the energy available in the atmosphere. This idea, though stimulating, still needs to be confirmed. Even without this 7th deleted installment, it should be remembered that the intense greenhouse effect of Venus and its storms constantly fuel a complex atmospheric chemistry. This dynamic could explain the rapid formation or sudden disappearance of certain compounds, which reinforces the interest of these recent discoveries. It is in this context that the launch of the Venus LifeFinder mission will take place in January 2025, initiated by Rocket Lab. This brief but ambitious operation will consist of collecting samples in the cloud region to identify possible organic traces or chemical anomalies. A module designed to traverse the dense Venusian atmosphere will collect data in a few minutes before being destroyed by heat and pressure. Scientists are relying on these measurements to clarify the enigmas related to phosphine and ammonia. Other projects are being added to this exploration. The Da Vinci and Veritas missions, with launches planned around 2031, have been confirmed. Da Vinci will analyze Venus's atmosphere in detail, focusing on noble gases to understand its origin, its possible oceanic past, and the mechanisms that led to its current situation. Veritas, on the other hand, will map the surface with a high-precision radar to better understand the geology and tectonic movements of the planet. If these missions achieve their objectives, we could gain a fresh perspective on this twin sister of Earth, often considered malevolent. The data from Venus Life Finder, Da Vinci, Veritas, and terrestrial laboratories will form a solid foundation for understanding how Venus became so inhospitable. Ultimately, they might shed light on the fate of rocky planets when the climatic balance deteriorates. In the vast narrative of space exploration, Venus has long been relegated to the background, overshadowed by Mars. However, recent discoveries about its atmosphere rekindle interest in this world hidden beneath the clouds. The joint presence of phosphine and ammonia in the heated heights of its sky prompts researchers to consider forms of metabolism very different from what we know. Certainly, terrestrial life relies on water and moderate temperatures, two elements absent here. But a biosphere suspended in acidic droplets remains conceivable. Imagining that organisms protected by a special membrane could survive in a mist of sulfuric acid questions the limits of life. Research on extreme environments on our planet, such as acidic lakes or very hot springs, shows that living organisms can surprise. Venus, despite its apparent hostility, could offer niches where organic chemistry persists. Upcoming missions, new instruments, and renewed scientific attention may perhaps lead to a better understanding of this intense world. Humanity has never been so close to unlocking the secrets of a burning universe, where heat and acid may not necessarily mean sterility. The arid landscape of Mars evokes a vast desert. Yet, behind its apparent hostility, this planet harbors signs of complex chemistry and components that can spark our curiosity. For years, probes and rovers have traversed its rocky soil, exploring the rocks to extract clues about potential traces of life or unique geological processes. Analyses have confirmed that water once flowed on its surface, giving way to brines and very particular minerals. Since the beginning of the century, NASA has been sending specially designed rovers to explore the Martian soil. The Perseverance rover, active in the Jezero crater, identified intriguing organic patterns in July 2024, dubbed leopard spots. These dark, rounded marks on certain rocks evoke a mottled coat. This discovery has raised new questions about their origin and the geological evolution of the planet. Scientists use the term organic compounds to refer to carbon-containing molecules, essential to known life. On Mars, their detection raises a debate. Do they come from ancient microorganisms or simple mineral processes? These signatures could originate from non-biological chemistry generated by past radiation or volcanism. Their very existence warrants further research. The Martian soil contains salts capable of producing very specific aqueous solutions. Perchlorate brines, formed from water and chlorine and oxygen-based compounds, remain liquid at extremely low temperatures, well below zero. They could survive sheltered from light in rock pores or deep cracks, creating an environment favorable to complex chemical reactions. In 2025, analyses caught attention. Methane peaks detected in the Martian atmosphere could be due to a phenomenon called barometric degassing. This gas, made of carbon and hydrogen, had already been observed, but its origin remained uncertain. Was it released by organisms hidden below the surface, or produced by mineral reactions? New data points to a release influenced by pressure variations. Barometric degassing results from pressure changes that occur when temperature varies greatly between day and night. On Mars, these differences are extreme, about 20 degrees or 36 degrees Celsius at the warmest, and sometimes less than -100 or -148 degrees Celsius at night. These fluctuations cause expansion or contraction of gases below the surface. When an opening is created, methane can suddenly escape, which would explain the observed peaks. As rovers continue their exploration, a new mission is underway, that of the European Space Agency, named Rosalind Franklin. Scheduled for 2028, it will examine the oxyoplanum region, rich in clays and perchlorate salts. This site could harbor brines protected from the cold. The rover will drill into the soil to search for traces of ancient water or biological activity, past or present. Oxyoplanum is characterized by deposits that are billions of years old. Scientists estimate that this plain may have been covered by shallow waters, favoring the preservation of organic matter. As these waters evaporated, they would have concentrated salts, forming perchlorates. Rosalind Franklin is equipped with a drill capable of reaching 2 meters or 6 feet of depth, where sediments are better preserved from radiation. In parallel, the Mars Sample Return Program is advancing. It plans to bring back to Earth samples collected by Perseverance for precise analysis. The tools on board the rovers remain limited. In the laboratory, the resolution is much finer. If all goes as planned, the return could take place around 2033, opening a new chapter in Martian exploration. The next decade will see collaborations intensifying. The increasingly powerful instruments, whether in orbit or on the ground, analyze the soil composition, the gases present, and the interior of Mars. Each discovery reinforces the idea that it experienced a more temperate past, marked by water. Understanding this history could shed light on the question of the origin of life. Mars remains a planet of many secrets. The leopard spots spotted by Perseverance, the methane peaks linked to barometric degassing, and future explorations of oxyoplanum reflect our desire to uncover its mysteries. The return of samples also promises to revolutionize our understanding. Between the orbits of Mars and Jupiter stretches a vast region filled with thousands of celestial bodies. This is the asteroid belt. Among them, Ceres holds a special place. The largest object in this zone, it is also classified as a dwarf planet. Discovered centuries ago, Ceres continues to intrigue with its nature, composition, and the phenomena that animate it. Today, data from space missions and ongoing research offer us a new perspective on this celestial body, situated between rocky worlds and small planetoids. In this part of our journey, we will explore the asteroid belt, focus on Ceres, and decipher the clues revealed by several probes, such as Dawn, the Cerescope project, and the OSIRIS-REx mission. Our exploration begins with a reminder. The Dawn probe, launched in 2007, was tasked with studying Vesta and Ceres. After a year around Vesta, it headed towards Ceres, reaching it in 2015. It observed its surface, measured its gravitational field, and sent data until the end of its mission in 2018. These records have since been meticulously analyzed. A new study campaign, scheduled for 2025, will revive the examination of these archives in hopes of better understanding the processes at work on Ceres. One of the most astonishing phenomena revealed by Dawn is cryovolcanism. On Earth, volcanoes emit burning lava. On Ceres, it involves an upwelling of cold liquid, a mixture of saltwater, rock salt, and ammonium. These brines, under pressure, seep from the subsurface. Traces of them are found in the Akator crater, leftovers left by their evaporation. This phenomenon is considered recent on a geological scale, less than 2 million years. This shows that Ceres is still active. The Kuiper crater, about 100 kilometers or 62 miles wide, features bright spots at its center. At the time of dawn, these luminous points surprised researchers. They turned out to be salt deposits resulting from the upwelling of enriched water. Recent analysis of the data also indicates the presence of ammonium, a form of nitrogen. Its discovery suggests the existence of underground reservoirs capable of storing and transporting various chemical elements. Understanding these sources and their movements is now a priority. To go further, the Spacecraft project is under development. It is slated for launch in 2029 with an orbiter equipped with a radar and a drill. The radar would send signals into the ground to detect internal structures. The drill would collect samples up to 50 meters or 164 feet deep. This would confirm the presence of brines, measure their concentration, and determine their composition. Such a mission would provide concrete clues about Ceres' internal activity. Reaching Ceres remains a challenge. It is located in a dimly lit region and possesses its own gravity. The probe will have to slow down, insert into orbit, and withstand surrounding particles. Engineers are therefore working on a reliable propulsion system and effective shielding. If these challenges are met, the reward will be substantial, understanding how such a small body could retain subterranean activity. In parallel, other missions are focusing on carbon-rich asteroids. OSIRIS-REx, launched in 2016, studied Bennu, a dark and ancient asteroid. After mapping its surface, it collected a sample in 2020. This will be examined in a laboratory on Earth. The goal, to understand its mineral and organic composition with a precision impossible to achieve in space. The first remote analyses showed the presence of hydrated minerals in Bennu's dust. These minerals contain water molecules trapped in their structure. This suggests that Bennu has been in contact with water, either in its own past or through collisions with other bodies. The hypothesis of enrichment from elsewhere is also considered. These discoveries prompt reflection on the chemical complexity of asteroid belt objects. By correlating these results with those from Ceres, a trend emerges. Water, salts, and carbon materials are present in bodies of various sizes. The distinction between asteroid and dwarf planet becomes less clear. Some of these objects may even have played a role in the Earth's history by bringing essential elements for life. Thanks to the samples from Bennu, researchers will be able to refine the inventory of volatile compounds, hydrated minerals, and complex organic molecules. The results, expected in the second half of the decade, will complement the lessons learned from Dawn's data. Together, these elements will build a more accurate portrait of the geological and chemical evolution of this area of the solar system. In the background, the question of resources looms. The water, salts, and carbon compounds detected on Ceres or Bennu are of interest. Some envision someday exploiting these resources in space. This raises technical challenges, as these bodies are not static. The cryovolcanic activity of Ceres, for example, could influence any industrial operation. For now, the ongoing missions remain scientific. Spacecraft, for instance, aims to better understand the internal composition of Ceres. The orbiter would map the subsurface, then release a module capable of drilling up to 50 meters or 164 feet deep. The collected data would allow measurement of ice, salts, and ammonium concentrations. Such an analysis would provide answers on how water could have persisted in this tiny world. All these discoveries are part of a broader vision, that of the evolution of the solar system. In distant regions, icy satellites sometimes exhibit internal movements, caused by gravitational forces. On Ceres, the heat may come from residual radioactivity, internal pressure, or the presence of salts that lower the freezing point of water. Asteroid impacts could also have played a role. Upcoming analyses will help clarify these mechanisms. Asteroids like Bennu, described as primitive, have changed little since the birth of the solar system. If they contain hydrated minerals, it will confirm that water is much more widespread than previously thought. It will remain to understand how these materials formed and integrated into their structure. In the years to come, the archives of Dawn, the measurements from Seerscope, and the samples from OSIRIS-REx will provide an overview of the geology and chemistry of several bodies in the belt. It will be a key moment for planetary astronomy. We might discover that salty water, salts, and ammonium have shaped these tiny worlds. In these seemingly frozen environments, the boundary between rock and liquid, between chemistry and geology, is much more subtle, and it's hundreds of millions of kilometers or miles from Earth in this still unknown territory that the next pages of our cosmic understanding are being written. Jupiter, located more than 770 million kilometers or 478 million miles from the Sun, dominates the solar system by its size. Its diameter is more than 11 times that of Earth. Its atmosphere, mainly composed of hydrogen and helium, is traversed by powerful currents forming colorful bands. This gas giant has long fueled myths, but today it is its physical properties and climatic phenomena that captivate researchers. Recent space missions immerse us in an ever-changing universe, revealing the intimate workings of this monumental planet. At the poles, Jupiter displays auroras of stunning intensity. In May 2025, the James Webb Space Telescope detected a polar aurora far brighter than those on Earth. Auroras are born from the encounter between particles from the Sun and a planet's magnetic field. But on Jupiter, the magnetic force enhances these interactions, causing light displays far beyond what we know. The solar wind, consisting of charged particles ejected by the Sun, strikes Jupiter at high speed. The planet's rapid rotation, in less than 10 hours, amplifies its magnetic field, increasing collisions in the atmosphere. Electrical currents then form up to the high layers, where they trigger powerful light emissions. Thanks to the instruments of the James Webb Telescope, researchers are gradually deciphering these unprecedentedly large light arcs. The Juno probe, in orbit since 2016, offers us a close-up and detailed view of Jupiter. With each pass near the clouds, it collects measurements on the magnetic field. During its 59th flyby, it revealed a more complex internal structure than expected, suggesting a core with diffuse boundaries. The boundary between the internal and external layers would be much more gradual than imagined. This diffuse core is an area where heavy elements slowly mix with hydrogen, transformed by extreme pressure. At these depths, the matter becomes electrically conductive. Once thought distinct, the transition to this state is now seen as more gradual. This discovery forces a rethink of the formation of giant planets and alters our understanding of internal mechanisms. The Juno team also exploits variations in the gravitational field to estimate the distribution of masses. Tiny changes in the spacecraft's trajectory provide clues about the core's density. The data reveal that heavy elements are spread over a large area, challenging the old models of Jupiter's formation. The JUICE mission, launched by the European Space Agency in 2023, is about to embark on a long journey. Starting in 2025, Its trajectory is precisely adjusted to ensure its arrival in 2031, where it will notably fly over Ganymede. This moon, the largest in the solar system, has its own magnetic field. The ongoing adjustments aim to secure the spacecraft's path despite the powerful attraction of Jupiter and its moons. JUICE will focus on Ganymede, as well as Europa and Callisto. It will have to withstand the strong radiation of the Jovian environment. The instruments on board are designed to operate despite exposure to energetic particles. This mission complements Juno's, and together they will provide valuable information on the atmosphere, magnetism, and potential habitability of the moons. The combined data from Juno and JUICE will help model the interactions between Jupiter and its satellites. While Juno examines the planet's interior, JUICE will map the magnetic fields and icy surfaces. Images taken from Earth and by James Webb will complete this picture. Together, they will allow the understanding of this planetary system's evolution. Imagine a world constantly shaken by eruptions more powerful than anything known elsewhere. This world is Io, the moon closest to Jupiter among those discovered by Galileo. Its surface, streaked with yellow, red, and black hues, is sculpted by relentless volcanic activity. To better understand its source, the Juno mission deployed a valuable instrument, GRAM, the infrared spectrometer that reveals the hottest areas of this raging moon. Io's volcanic activity was discovered in the 1970s, thanks to images transmitted by the Voyager probes. Jets of material soared to impressive altitudes, to general surprise. Since then, astronomers have multiplied their observations. They have noted that Io's volcanoes awaken at irregular intervals, releasing sulfur and sulfur dioxide. Today, Juno is approaching the moon to probe the heat sources hidden beneath its surface. GRAM, initially designed to study Jupiter's auroras, has proven valuable for analyzing Io. It maps the hottest spots on the surface by detecting infrared variations. Some areas show temperatures above 727 degrees Celsius or 1,341 degrees Fahrenheit, signaling extraordinary volcanic activity. Such heat reveals the power unleashed within the moon itself. This extreme temperature demonstrates the unique nature of Io. Its volcanism is powered by the gravitational forces of Jupiter and its neighboring moons. In orbit, Io is constantly stretched, compressed, and heated. Its interior deforms, generating enormous energy. This phenomenon is often compared to a balloon pressed at regular intervals, releasing its heat through eruptions. According to NASA, some of these eruptions produce more energy than all of Earth's power plants combined. Among Io's most spectacular sights, Loki Patera stands out. It is a vast depression filled with molten lava, about 200 kilometers or 124 miles wide. Its name evokes the changing and unpredictable nature of this place. Recent analyses confirm that it is a lava lake, fed by pressurized internal reservoirs. When the crust gives way, the lava surges forcefully, illuminating this already turbulent surface. A lava lake forms when internal heat melts rocks in deep layers. Magma accumulates in cavities. If the pressure becomes too strong, a fissure opens and magma gushes out. At Loki Patera, this cycle repeats. The crust solidifies, then gives way under the heat. These regular movements trigger impressive eruptions. This dynamic has been confirmed through infrared imaging and simulations. Periodically, hotter lava waves move through, overturning the frozen crust and revealing the magma beneath. This thermal overturn is at the heart of Io's volcanic activity. Each phase of eruption unveils the buried power within its depths. Researchers are pondering the energy released. Estimates show that certain eruptions at Loki Patera far exceed the energy capacity of all Earth's installations combined. The lava reaches extreme temperatures. Its composition, rich in silicates like olivine or pyroxene, explains these extreme heat levels. This activity underscores how Io is a distinct object. Understanding Io's volcanism allows us to explore the dynamics of the Jovian system. By analyzing this moon so close to a massive planet, researchers decode how heat is distributed inside a celestial body. Juno, with its sensors, will continue studying these hotspots. This exploration reveals an ever-changing landscape, a vibrant testament to cosmic energy. Each discovery shows that Io still holds many mysteries. In this roiling world, science advances step by step. Europa, one of Jupiter's major moons, is considered one of the best candidates to harbor life beyond Earth. Astronomers believe it holds a vast liquid ocean hidden beneath a thick ice crust. Clues suggest that this ocean might be in direct contact with a rocky core, an important condition for the development of biological processes. Its surface, marked by a network of fractures, colored streaks, and chaotic zones, perhaps reveals ongoing exchanges between subsurface water and space. The recent observation of carbon dioxide in the Terra Regio region, spotted by the James Webb Telescope, reinforces this hypothesis. The James Webb Space Telescope, launched in late 2021, observes the universe in the infrared. Its large mirror captures the faint light of distant objects. Thanks to this precision, it identified the presence of carbon dioxide at Terra Regio, likely originating from Europa's hidden ocean. This deep origin suggests a link between the internal layers and the icy surface, rather than mere external contamination, an essential discovery. To understand the importance of this detection, one must remember that carbon dioxide is linked to geological or biological processes. On Europa, its presence in an active zone could indicate chemical transfer between the subsurface water and the upper layers. Researchers think this region experienced an upwelling of materials, partially melting the ice and depositing ocean-derived compounds on the surface. The carbon dioxide frozen on the surface would be a residue of this process. This appearance on the surface poses an essential question. Does the ocean harbor other substances capable of sustaining life? If the water comes into contact with rocks at the bottom, reactions similar to those observed in Earth's oceans could occur. On Earth, hydrothermal vents release enough chemical energy to support life forms. If a similar phenomenon exists under Europa's ice, then this carbon dioxide is just one clue among others of an active world. It's to delve deeper into these avenues that the Europa Clipper mission was conceived. Scheduled for a 2024 launch, it will explore the moon from all angles. 49 flybys are planned between 2030 and 2033, each aiming to gather data on surface, internal structure, geology, and atmosphere. Radars will probe the ice, spectrometers will analyze chemical compounds, and cameras will detail fractures and potential fluid upwellings. probe will also be equipped to detect potential plumes of vapor bursting through the ice. Some evidence observed from the Hubble telescope suggests such geysers exist. If confirmed, they could carry ocean particles, allowing for direct analysis without drilling. Understanding how these plumes operate would also shed light on surface renewal. The discovery of carbon dioxide in Terra Regio could be a sign that these phenomena are frequent. If plumes are observed, the onboard instruments will analyze the molecules they carry. Scientists hope to find other gases like methane or ammonia resulting from deep chemical reactions. One of Europa Clipper's goals is also to map the ice to assess the ocean's depth and identify possible pockets of water between the surface and the lower layers. This information will help understand internal circulations and areas of weakness. Technically, the probe will operate thanks to large solar panels capable of capturing light at this distance. It will also use powerful communication systems to send data back to Earth. Each flyby will be optimized to collect as much information as possible, with trajectories calculated to skim the most promising areas. With this method, Europa Clipper will be able to create a detailed map and connect observations around key regions like Terra Regio. The gathered data will help assess the conditions for a future mission on site, perhaps with a lander or a drilling robot. Even though no such project is yet validated, interest in Europa continues to grow. Researchers hope that analyses will help clarify the ocean's chemistry, internal temperature, and the depth at which life could exist. This quest awakens the hope of one day discovering a form of life hidden beneath Europa's ice. Ganymede is one of Jupiter's 4 largest moons, and the largest of all those orbiting the Sun. Its diameter even exceeds that of Mercury, making it a remarkable celestial body. Calm in appearance, with its bumpy terrain and icy surface, it nonetheless hides a deep ocean beneath its crust. Over the decades, evidence has accumulated until this hypothesis was confirmed, making Ganymede a major target for studying environments that could harbor life. Its uniqueness is further enhanced by the presence of its own magnetic field, a unique feature among known moons. Current missions aim to explore this singularity and further analyze its internal structure. The Juno probe, launched towards Jupiter, carries a magnetometer capable of precisely measuring Ganymede's magnetic environment. This instrument studies the intensity and orientation of magnetic fields and helps understand how charged particles interact with the Moon. Although designed to analyze Jupiter's magnetosphere, this sensor has also provided a unique glimpse of Ganymede's magnetism during its flybys. The collected data reveals the presence of currents called Birkeland currents, flows of electrons and ions circulating along magnetic lines between Jupiter and Ganymede. These energetic exchanges, already observed in other planetary contexts, confirm that the Moon maintains a stable magnetic field and that it is dynamically connected to its environment. They bear witness to powerful electromagnetic interactions, where moving particles can generate luminous and electrodynamic phenomena. Ganymede's magnetic field is thought to be generated by a metallic core, rich in iron and nickel. This partially liquid core produces a dynamo effect, leading to the emergence of a global magnetic field. Juno's measurements also suggest the existence of several conductive layers beneath the surface, particularly a salty ocean composed of layers of water enriched with salts, separated by ice layers, each possessing their own electrical properties. This internal ocean, composed of salty water similar to sodium chloride or magnesium chloride solutions, interacts with Jupiter's magnetic field and produces induced currents. These electrical movements complement those of the core to shape Ganymede's overall magnetic signature. Confirmation of these processes refines our understanding of its internal structure and the stability of its magnetic field over the long term. In this view, the European JUICE mission for Jupiter Icy Moons Explorer plans to study Jupiter and several of its moons, with Ganymede as a priority. It carries a radar specially designed to explore ice in depth, named Radar for Icy Moons. Exploration, or RIME, this instrument will be able to probe the icy crust up to 9 kilometers or 6 miles, depending on soil composition and ice purity. This radar sends radio waves through the ice. When these waves encounter an interface, such as the transition from ice to water, they bounce back and return a signal that allows mapping the internal structure. Like a giant ultrasound, RIME will draw a vertical cross-section of the moon, revealing the arrangement of the frozen layers and any liquid reservoirs. This type of observation will be essential to confirm the existence of conductive layers. Scientists believe that each layer of water may contain different concentrations of salts, influenced by exchanges with deep rocks or upper layers. These studies will deepen the chemical understanding of Ganymede. The temperatures measured vary significantly between the areas plunged in shadow, close to minus 150 degrees Celsius or minus 230 Fahrenheit, and the areas exposed to light being more moderate. This thermal contrast, combined with internal pressure, makes it possible for liquid water to be maintained under the frozen crust. But beyond the structure, what also interests researchers is the potential of these salty oceans to host complex chemical reactions. In the presence of organic molecules and energy, the conditions could bring together the basic ingredients of life. Although it's still too early to mention biology, this moon remains at the heart of astrobiological research. The detected Berkelian currents, along with a very tenuous oxygen-rich exosphere, highlight the dynamism of Ganymede. The electrons and ions in circulation interact with this thin, gaseous envelope, revealing continuous physical activity. Ganymede is therefore not just a simple frozen block, but a natural laboratory where the interaction between a lunar magnetic field and the magnetospheric environment of a giant planet takes place. The JUICE mission will deepen this portrait by crossing data from the RIME radar with those from other instruments on board. Spectrometers will analyze the light to identify chemical signatures, and cameras will observe the topography in detail. Together, these tools will help reconstruct the internal functioning of Ganymede. Diving 9 kilometers or 6 miles deep represents a major technical challenge. It's necessary to balance the power of the signals, the sensitivity of the receivers, and the available energy. The composition of the ice can attenuate the waves, complicating the interpretation of the data. Engineers have thus designed sophisticated systems capable of isolating useful signals from surrounding noise. The insights gained from Juno have already highlighted a more complex magnetic field than expected, with conductive water layers separated by dense ice. Some theories even consider the presence of high-pressure ice, stable only at extreme depths. The arrival of JUICE at Ganymede will offer an unprecedented opportunity to verify these hypotheses. Its radar will locate the boundaries between ice and liquid water and assess the depth of these layers. This complete portrait of the lunar interior will enable estimating the amount of water present. Questions remain about the dynamics of these layers and the circulation of water, the heat of the core, internal pressure, possible surface faults, all factors influencing the stability of the magnetic field and the behavior of the ocean. Combined data from Juno and JUICE will help uncover the secrets of this singular moon, hidden in the shadow of Jupiter, yet with its own identity. The analysis of currents detected by Juno and the exploration of the internal structure by JUICE are gradually drawing the image of a complex world. Ganymede is not limited to a frozen satellite. It is a distinct dynamic object, harboring a deep, salty ocean and an active magnetic field. Thanks to future observations from the RIME radar, researchers hope to unlock the mysteries of this fascinating moon and better understand the diversity of lunar environments in our solar system. Callisto is often described as the forgotten moon of the Jovian system. Farther than the other large moons of Jupiter, it intrigues with its complex history and marked surface. Viewed from a distance, it seems frozen, covered in craters and ice mixed with dark minerals. But behind this apparent immobility, geological and chemical clues reveal past and perhaps even present activity. Recently, the James Webb Space Telescope detected an uneven distribution of carbon dioxide ice on its surface, suggesting dynamics much subtler than previously imagined. Before exploring the implications, it's essential to revisit the major milestones that have shaped our understanding of Callisto. The moon was first observed in the early 17th century by Galileo Galilei. At the time, his instruments couldn't distinguish its details. Callisto appeared as a simple bright spot accompanying Jupiter. The following centuries slowly unveiled its peculiarities thanks to technological advances in space missions. Long considered a block of inert ice and rock, Callisto revealed itself to be more complex than expected. Some gravitational and magnetic data hinted at the possibility of a structured interior, even a liquid layer buried beneath its icy crust. In 2025, the most sensitive observation instruments continue to explore this mysterious moon. The James Webb Space Telescope, observing in the infrared, detected unexpected chemical signatures. Among them, carbon dioxide ice appears in a localized manner, concentrated in certain areas, absent in others. This non-uniform spatial pattern indicates that recent processes, such as impacts or internal upwellings, might still mark the surface. This single detail rekindles the debate on Callisto's geological activity. Carbon dioxide is a common gas on Earth, but in Callisto's icy environment, it condenses and forms stable ice in the coldest regions. For such ice to appear on the surface, a relatively recent supply is needed. Researchers propose several explanations: collisions with small bodies containing gas, or the release of carbon dioxide from deep layers through briefly opened cracks. In any case, this fragmented presence challenges the idea of a completely frozen moon. An impact, even a modest one, can suffice to transform a local landscape. When an object collides with Callisto, it releases a large amount of energy. The impact produces heat, ejections of dust and ice, and can lead to the emission or capture of gas. As they cool, some of these elements, including carbon dioxide, settle on the surface. The analysis of this ice's distribution shows it often coincides with circular structures associated with recent craters, reinforcing the idea of still visible sporadic events on a geological scale. But that's not all. Beyond impacts, some researchers suspect the existence of buried water pockets. Even if Callisto seems inert, data suggests that internal areas could contain liquid water, maintained by residual core heat. This water wouldn't be warm in the usual sense, but tepid, sometimes reaching temperatures close to 0 degrees Celsius, or 32 degrees Fahrenheit. In such an environment, it's enough to keep the water in a liquid state, radically changing the perception of this moon. Here's where the concept of diapir comes into play. A diapir refers to the slow ascent of a warmer and less dense material through cooler, rigid layers. On Callisto, it could be ice enriched with water, or lighter materials that migrate to the surface, creating underground domes. If these structures exist, they could cause surface deformations, open cracks, and allow gases to escape. This would explain some of the irregularities observed in the distribution of carbon dioxide. To test this hypothesis, scientists analyze local gravity, topography, and the propagation of radio waves as they skimp or cross the moon. These measurements could reveal anomalies, such as density variations or signs of internal activity. Although Callisto hasn't yet been the subject of a dedicated mission, this research draws attention. As evidence of subterranean structures accumulates, interest in this so-called secondary moon keeps growing. This renewed attention is also due to a fundamental question, that of life. Even a pocket of warm water, enriched with some nutrients and isolated in a stable environment, can represent a potential ecosystem. If Callisto harbors such an environment, no matter how modest, that is enough to justify extensive research. The elements necessary for life, such as water, energy, and simple chemical compounds, could be present. Nothing has yet been proven, but this possibility is enough to rekindle scientific curiosity. Thus, the recently identified carbon dioxide ice becomes an indication among others. It could result from an impact, an underground uprising, or a combination of both. Observational techniques are progressing, and infrared already allows for a better distinction of the surface composition and temperature. Any detected anomaly, even minor, becomes a foundation for new hypotheses. But the precision remains limited, and future measurements will be necessary to confirm these leads. Once perceived as frozen, Callisto is beginning to reveal a more nuanced story. An ancient surface, but perhaps crossed by discrete internal forces. Evidence of active ice, released gases, and perhaps pockets of water in depth. What was believed to be a dead moon is gradually becoming the scene of discrete, yet real processes. Researchers hope that the coming years will allow them to track these phenomena over time. Distant flybys or next-generation telescopes could refine the maps of carbon dioxide distribution and track their evolution. The presence of water will need to be confirmed, perhaps through gravitational measurements or radar-sounding instruments. And if one day a lander sets down on Callisto, it may finally pierce the ice to reveal secrets buried for billions of years. Callisto, long relegated to the background, is revealed today as a world that could still surprise. Its cratered surface, scattered ice deposits, and hints of internal movements paint a new picture. In the icy depths of this distant moon, fragments of geological history may still be in motion. And with each observation, our understanding deepens, confirming that the universe still has many secrets to offer us. Saturn, the giant planet outside the solar system, has always captivated with its allure. Its immense and bright rings resemble a celestial work suspended. But above its clouds, a much more fragile phenomenon is playing out. Ongoing studies reveal that these rings, made of ice and a bit of dust, are gradually falling onto the planet. This phenomenon is called ring rain. They are icy particles attracted by gravity and electromagnetic fields, plunging into the atmosphere. It is estimated that about 10 tons, or 22,046 lbs, of ice per second plummet there. The idea that these structures could lose so much matter is awe-inspiring. The rings were once thought to be immutable or very ancient, but this rapid descent forces a re-evaluation of their history. Their disappearance could occur in less than 100 million years. On a cosmic scale, it's brief, but compared to our human benchmarks, it remains vertiginous. Considering the age of the solar system, these rings now appear as transient formations. To understand this estimation, one must examine the composition of the rings. They are primarily made of water ice, similar to that observed in winter on Earth, but on a gigantic scale. These particles are organized into distinct rings, classified by letters according to their location and brightness. From a distance, a regular disk is perceived. Up close, variations in density, clear divisions, and spiral patterns can be observed. The grains range from dust to blocks several meters or yards across. They are subjected to multiple forces: the gravity of Saturn and its moons, solar radiation, and ionization effects. These interactions push certain particles toward the upper atmosphere. This mechanism, influenced by the magnetic field and seasonal cycle, explains the ring rain closely monitored as the year 2025 approaches. Scientists are finalizing a study to estimate the lost mass. They use telescopic data cross-referenced with those from the Cassini mission, which extensively explored Saturn. Although completed, this mission provided a wealth of clues about the composition of the rings and their density. These data enable the modeling of the constant exchange between the icy disk and the atmosphere. The loss flow is estimated at 10 tons, 22,046 lbs, of ice per second. If this rate is projected over time, Saturn's iconic architecture could radically transform in 100 million years. It would be the end of a major visual chapter in its history. Another essential question concerns the temperature of these ice arcs. In addition to gravity, the sun and charged winds influence their descent. To learn more, scientists rely on the James Webb Space Telescope and its MIRI instrument. This infrared camera captures the heat of distant objects, even those that are not very warm. To the human eye, the ice reflects light, but it remains very cold. Cassini recorded moderate daytime temperatures, which drop at night. MIRI should allow for a fine mapping of these temperatures and reveal how they vary with Saturn's seasons. Saturn's seasons are long. A year there lasts nearly 30 Earth years. The slow change in sunlight modifies the ring's illumination. Some receive more light for years, others less. This influences the heat absorbed and re-emitted by the ice. Dark areas remain cold, altering the ice structure. This temperature variation could explain the increased fragility of certain areas. MIRI's new thermal maps could unveil links between temperature and the intensity of ring rainfall. Researchers will compare these readings with older ones to detect changes in the most affected sectors. Initial results show that the seasonal variation is more pronounced than expected. Some segments warm up faster, producing more vapor or ions. When water vaporizes, it can turn into charged particles, which then fall into the atmosphere. Temperature and electromagnetism together control this movement of crystals. By monitoring each region for years, researchers hope to understand if the mass loss remains stable or varies with the season. Early models suggest that certain peaks in icy precipitation could coincide with Saturn's seasonal tilt. Beyond this disappearance, understanding these mechanisms allows exploring the origin of the rings. Several theories compete. Destroyed icy moon, captured comet, scattered debris. The fact that they are losing mass points to a recent origin. This raises a question. Why does Saturn, and not the other giants, possess such a network? Their rapid evolution suggests a temporary phenomenon, born of a violent event not long ago. The constant rain would be the last act of a story that began a few 100 million years ago. In the coming years, the cross-study of the rain and temperatures will provide a fresh perspective on these rings. Combined with the expected report, it will allow adjustments to estimates of their disappearance. Current models, although advanced, remain to be refined. Only prolonged observations will confirm whether the ice belt will disappear in less than 100 million years. In the laboratory, experiments subject ice to ion beams to reproduce Saturn's conditions. These tests refine our understanding of the forces interweaving magnetism, heat, light, and matter. If Saturn deserves the title of Lord of the Rings, nothing guarantees it will keep it. This jewel could fade away. For us, it is a unique opportunity to contemplate a structure in full mutation. The upcoming data from the Webb Telescope and its MIRI instrument will detail this transformation. The better we understand these variations, the clearer our reading of the ring rainfall will be. In the near future, Saturn might display only a few frozen mists, or perhaps we will discover a complexity that will prolong the splendor of its arcs. The year 2025 will bring us closer to this truth. For humans, it will be a privileged moment of observation of a constantly evolving universe. In the icy expanses of Saturn's system, Enceladus captures attention. Despite its small size, this moon has intrigued scientists since the Cassini mission observed its geysers spewing into space. New analyses now reveal the presence of sodium phosphates with a phosphorus concentration 100 times higher than in our oceans. To grasp the magnitude of this discovery, one must understand what a geyser on Enceladus is. It consists of jets of water mixed with minerals and volatile compounds escaping through fractures at the South Pole. This ejection is driven by the pressure of the internal ocean, kept warm thanks to Saturn's gravitational pull. These plumes carry with them elements that reveal the moon's internal composition. Phosphorus is essential to life. On Earth, it is part of the formation of vital molecules like nucleic acids or ATP. It comes from rock erosion and is then transported to the oceans. On Enceladus, its detection in geysers suggests that comparable reactions are occurring in its depths and that active chemical processes are ongoing there. Scientists are questioning the stability of such a high phosphorus concentration. Geochemical models indicate that underground water could dissolve phosphorus upon contact with internal rocks. The chemical environment, rich in bicarbonates and other alkaline components, would favor phosphate formation. This activity would be maintained by the heat resulting from gravitational tensions between Enceladus and Saturn. geysers, true windows into this hidden world, project water, ice, and minerals. Cassini's instruments detected the chemical signature of these emissions. Today, more recent analyses confirm the presence of sodium phosphates, reinforcing the hypothesis of a chemically active and potentially habitable internal ocean. Habitability implies the presence of life-favorable elements. On Earth, phosphorus is a key nutrient. Its presence combined with hydrothermal sources suggests that Enceladus could provide conditions compatible with microscopic life forms. But to verify this, on-site studies will be necessary. For this purpose, the Enceladus Orbilander mission is considered. Planned for 2033, it aims to place a spacecraft in orbit, then make it land. The goal is twofold: collect data from a distance and conduct direct observations on the surface. This mission will seek to unravel the mysteries of the underground ocean and analyze the geysers. But this project faces several challenges. Stabilizing around a small moon requires precise maneuvers. Engineers must design instruments capable of withstanding extreme conditions with very low temperatures and an environment saturated with particles. Years of design will be needed before its launch. Once there, the Orbilander will closely study the plumes. Cameras and spectrometers will measure the composition of the vapors and particles. During landing, the device will approach active fractures to collect samples and study the icy surface. The search for biosignatures will be central. Scientists hope to find amino acids, lipids, or other organic compounds. Isotope analysis will help understand the chemical reactions. If organisms consume certain substances, they leave characteristic traces. Such a discovery would change our perception of life in the universe. But beyond this quest, Enceladus also enlightens us about the dynamics of icy moons. The exchanges between water, rock, and salts reveal the internal structure, heat circulation, and the maintenance of the ocean beneath the frozen crust. The geysers also influence the formation of Saturn's E-ring. Laboratory experiments simulate this complex chemistry. By replicating Enceladus's conditions, researchers test the stability of phosphates and their interactions with other elements. These works, compared to mission data, refine our understanding of environments where life could emerge. In this fascinating exploration, we focus on Saturn's most massive moon, Titan. Though distant from our sun, it stands out as an enigmatic world with a dense atmosphere, unique landscapes, and complex organic chemistry. We will detail how the James Webb Space Telescope has revealed the presence of a cation called C6H5+, considered a precursor to more elaborate molecules known as tholins, and discuss the mapping of methane lakes around the pole. We will also see how the future mission Dragonfly, scheduled for launch in 2028, aims to land in a specific area called Selk Crater by 2035, a crucial step in better understanding the conditions on Titan's surface. Let's start by recalling that Titan is covered in a particularly thick atmosphere, mostly composed of nitrogen, similar to Earth's, although the surface pressure is slightly higher. This feature makes Titan unique among the moons of the solar system, as most do not possess such a developed atmosphere. The shadow of the sun is faint there, and temperatures hover around minus 180 degrees Celsius, or minus 296 degrees Fahrenheit. At these levels of cold, many gases become liquid, and some compounds change behavior. It is in this icy and hazy setting that astonishing organic chemistry takes shape. The recent discovery by the James Webb Telescope surprised scientists. The identification of this ionized molecule, the cation C6H5+. This cation, similar to a benzene ring core deprived of an electron, is considered a key intermediate in the formation of complex carbon molecules. Tholins, for example, are organic substances present in Titan's upper atmosphere. They give it its orange tint. Researchers estimate that these tholins form from simple elements like this cation before assembling into larger structures. Studying these processes is essential to understanding the origin of organic molecules throughout the solar system. To simplify the role of this cation, let's imagine a construction chain where each brick forms a larger molecule. The C6H5+ is one of these bricks. Thanks to certain photochemical reactions, stimulated by sunlight, even weakened by distance, it combines with other fragments containing carbon and hydrogen. Gradually, tholins appear, brownish or orangish matter, widespread in the atmosphere and possibly on the surface. These tholins could play a role in prebiotic chemistry, that which precedes the appearance of life. Studying Titan thus becomes observing a natural laboratory where molecules form under extreme conditions, far from our daily experience. Another striking result concerns the distribution of methane lakes, notably around the North Pole. Thanks to recent data, it has been possible to map more than 98% of these liquid reservoirs, mostly composed of methane. On Earth, this gas is flammable, but on Titan, at these temperatures, it liquefies and forms actual seas. This discovery confirms the existence of a methane cycle similar to the water cycle on Earth: evaporation, cloud formation, precipitation. This active climate, although very different from ours, shows meteorological dynamics. Radar and infrared images also show the possible presence of channels, underground reservoirs, and terrains shaped by liquid rain. A human observer would see methane rain falling, not water, and discover that this liquid behaves like water on Earth. Interest in Titan is growing, and exploration is advancing. After the success of the Cassini probe, the scientific community launched an ambitious project, the Dragonfly mission. Scheduled for 2028, Dragonfly is a drone equipped with rotors. It will be able to fly from site to site instead of rolling like Martian rovers. The dense atmosphere and low gravity of Titan facilitate this mode of travel. It requires less power to fly a craft in this environment than here. In 2025, mission managers confirmed the landing site choice, Selk Crater. This crater, several tens of kilometers wide or miles wide, could contain various organic materials and signs of ancient activity. The impact that formed it may have brought deep layers to the surface. Dragonfly's instruments will analyze these samples on site to determine their chemical composition. The goal is to find complex molecules resulting from the transformation of the cation C6H5+ and other carbon compounds. Dragonfly will notably carry a mass spectrometer to analyze these materials. The objective is to understand how these chemical reactions interact with Titan's cold environment and what they can tell us about prebiotic chemistry. Some scientists even suggest the hypothesis that Titan could harbor a form of life without water, although this remains highly speculative. The study of Titan raises fundamental questions about the origin of organic chemistry in unexpected conditions. Technically, the mission presents many challenges. The journey to Titan will take several years. The landing will require a controlled approach with a perfectly calibrated descent to avoid any risk on a still largely unknown terrain. Aerodynamic laws are different there due to atmospheric density and extreme cold. The rotors, electronics, and batteries must be designed to operate around minus 180 degrees Celsius or minus 292 degrees Fahrenheit. Once operational, Dragonfly will advance with successive jumps, traveling several kilometers or miles before stopping to recharge and analyze. Its instruments will provide high-resolution images, measure the composition of the local atmosphere, and analyze the collected materials. These samples will be heated and examined in an internal device to identify molecules never observed elsewhere. The data will be sent to Earth via a powerful antenna, even though receiving them will take time. With these prospects, Titan appears as a unique natural laboratory. It features a fluid cycle based on methane and a wide range of organic compounds. The cation C6H5+ is just one element among others. Scientists consider Titan as one of the major targets for planetary exploration. Its study sheds light on organic chemistry in extreme environments, the evolution of atmospheres, and the possible formation of essential molecules for life on other worlds. The James Webb Telescope will continue to provide valuable data on Titan, notably by refining the detection of new molecules in its atmosphere. It will also observe the evolution of the seasons, which last several Earth years. The Dragonfly mission, meanwhile, promises to revolutionize our understanding. By studying the surface at Selk Crater, it could reveal the active chemistry of the subsurface. It may well be the first time a robot will fly in a foreign sky, probing an icy world shaped by methane rain. If the mission manages to land smoothly and collect varied samples, it could lead to major discoveries about organic chemistry. Some even hope to find the first clues of a chemistry of life. Even if life on Titan remains uncertain, understanding how these molecules assemble in this icy world will be invaluable for exobiology. We are faced with one of Saturn's most enigmatic moons, Mimas. Long considered a simple ice ball, with no remarkable relief except for its gigantic crater named Herschel, it has always intrigued scientists with its appearance. At first glance, this moon seems sterile, devoid of internal activity. However, new analyses from Cassini probe data, soon to be complemented by studies planned for 2024, reveal a much more fascinating story. At the heart of this discovery is the concept of libration, the slight wobbling of an astronomical body around its axis during its orbit. Astronomers closely examine the variations in speed and orientation of Mimas, as they provide clues about the distribution of its internal mass. In 2024, a series of precise observations and calculations will be dedicated to these movements to better understand the deep structure of this small moon. Preliminary studies already suggest that Mimas could harbor a global ocean, hidden beneath an ice layer estimated to be 20 kilometers, 12 miles thick. This ocean, at most 15 million years old, would therefore be young on the scale of the solar system. This revelation, relayed by several scientific works, reignites interest in this icy body. The presence of an ocean in such a small celestial body surprises many researchers, as its size seemed insufficient to maintain a source of internal heat. However, for an ocean to remain liquid, a moon must produce or conserve a certain amount of thermal energy. This energy can come from the decay of radioactive elements in the core or from tidal forces generated by Saturn and its other moons. In the case of Mimas, tidal forces seem to play a key role. As it orbits around Saturn, Its interior contracts and expands, which produces heat through friction. If this heat is sufficient, it would prevent the water from freezing. Measurements from Cassini, combined with analyses from 2024, will help determine if this mechanism can indeed sustain a liquid reservoir for several million years. To verify the presence of an ocean, scientists are refining their calculations of libration. If Mimas behaves like a solid block, its oscillations follow a predictable pattern. But if its core contains a liquid, then its movements will be different. These measurable deviations could provide proof that an ocean is hiding beneath the frozen crust. Another essential question concerns the salinity of this ocean. At these very low temperatures, close to minus 180 degrees Celsius, 292 degrees, the presence of certain salts is necessary to prevent the water from freezing. These compounds lower the freezing point and keep the water in a liquid state, but the nature, concentration, and origin of these salts remain unknown. To find out more, researchers will likely compare future gravitational and magnetic measurements of Mimas to those obtained on other icy moons. Differences in signatures will allow them to evaluate the density and composition of the ocean. Understanding the saline nature of this reservoir could shed light on the evolution of Mimas and its ability to maintain internal activity. The thermal stability of this ocean over millions of years is intriguing. If Mimas has maintained an ocean for 15 million years, how much longer might it persist? Will tidal forces intensify or diminish? Models indicate that small orbital changes and gravitational resonances with other moons could influence the survival of this ocean. To establish a realistic scenario, specialists are reconstructing the orbital history of Mimas. From its formation to today, it may have moved closer to or farther from Saturn. Each variation modifies the amount of internal heat released. If Mimas has migrated or been affected by other moons like Triton or Enceladus, these episodes could have triggered or hindered the formation of the ocean. Meanwhile, data from 2024 should refine our understanding of the crust. Is it homogeneous or crisscrossed with fractures? If fissures exist, then compounds from the depths might reach the surface and be detected by dedicated instruments. The question of life resurfaces in scientific discussions. Although Mimas seems less favorable to life than other moons like Enceladus or Europa, the presence of a liquid ocean, even a modest one buried under 20 kilometers, 12 miles, of ice, raises hopes of detecting organic compounds. Conditions are extreme, but nature can sometimes surprise us. If this ocean is confirmed, it could overturn our perception of icy moons. Mimas was thought too modest to contain a complex history. However, this possible discovery redefines its scientific priorities. It would encourage the launch of new missions to explore this moon, probe its ocean, analyze its composition, and understand its thermal evolution. Uranus is often described as the tipped-over planet due to its unusual tilt, but this is not its only peculiarity. To understand it, we must revisit its discovery, the peculiarities of its orbit, and the recent data collected thanks to advanced instruments like the James Webb Space Telescope. In this part of our journey through the solar system, we focus on one of the most enigmatic worlds. Let's embark on a detailed excursion, adopting the perspective of a passionate narrator to better understand Uranus, this tilted giant that still holds many surprises. When talking about Uranus in a historical context, we often start with its official discovery by William Herschel in 1781. At that time, it wasn't suspected that such a distant planet could be hiding in the depths of the sky. Telescopes were less powerful, knowledge of the solar system was limited, and the notion of an ice giant lying on its side was not yet conceivable. Although some astronomers had previously noted a wandering bright point, no one had identified it as a planet. Herschel's discovery marked a turning point in understanding our celestial neighborhood. Approaching Uranus fictively, one notices a troubling fact. Its axis of rotation is tilted about 98 degrees. Uranus rolls around the Sun instead of spinning upright like the other planets. This tilt, likely due to an ancient collision, gives Uranus extreme seasons. It takes 84 Earth years to complete a full revolution, which means that each pole remains in darkness or bathed in light for more than 40 years. Although these climatic conditions are unfamiliar, they intrigue researchers who attempt to understand their impact on Uranian meteorology. Seen from afar, Uranus appears uniform, a disk tinted blue and green. During the passage of Voyager 2 in 1986, few details were visible. But thanks to recent technologies, notably the infrared and ultraviolet detectors of the James Webb Space Telescope, our view has sharpened. We now distinguish 11 bright rings, far more visible than imagined. Discovered in the late 70s, these rings were already subtle, composed of dark particles and ice chunks. Their clarity in the new images is intriguing. The goal is to study their composition, density, and distribution to understand their origin, possibly linked to the fragmentation of an icy body. Among the latest data from the James Webb Space Telescope, the formation of a large polar cloud in the northern hemisphere as the solstice approaches is noted. On Uranus, this moment corresponds to the maximum tilt of a pole towards the Sun. The recent images show a large cloud rising in the atmosphere above the polar region. Researchers are questioning the temperature variations that could favor the condensation of certain molecules. The atmosphere, composed of hydrogen and helium, also contains methane at the origin of the blue-green tint. Understanding the behavior of these gases at -200 degrees Celsius or -328 degrees Fahrenheit is essential for analyzing this peculiar meteorology. Winds of several hundred meters per second or over 1,000 feet per second could fuel these cloud structures. Following Uranus and discerning its rings is not just an imaging exercise, it is a crucial step for future missions. The scientific community wants to learn more about the subsurface of Uranus and its magnetic field, known for being chaotic. During Voyager 2's flyby, this field already surprised with its skewed orientation. Since then, no probe has been specifically sent to Uranus, aside from some distant observations. This is why a project named the Uranus Orbiter and Probe is recommended for a launch in 2031. The aim would be to place an orbiter around the planet and send a probe into its atmosphere. Scientists hope to gather new data on the composition of the deep layers, the presence of water, internal dynamics, and magnetic activity. Measurements of pressure, temperature, and chemical tracers could reveal major elements about the chemistry and physics of ice giants. Uranus and Neptune are thus named because their atmospheres contain more ices than those of Jupiter or Saturn. Researchers want to understand their formation in the outer zone of the solar system. Interest in this project has increased, and a feasibility study is planned for 2025. The best trajectory, the resistance of the instruments to extreme conditions, and the overall cost must be determined. The journey to Uranus takes more than a decade, with several gravitational assists to gain speed. Once there, the orbiter will have to slow down and stabilize around Uranus. It will release a probe that, protected by a thermal shield, will penetrate the atmosphere. The onboard instruments will analyze the composition and perhaps the internal structure, with a mantle of water ice, ammonia, and methane surrounding a rocky core. This model could explain the magnetic anomalies. Studying Uranus allows us to better understand planetary formation and evolution elsewhere in the galaxy. Many discovered exoplanets are the size of Uranus or Neptune. Knowing this planet sheds light on the understanding of billions of others, perhaps similar. Beyond science, exploring Uranus reminds us that the universe is full of worlds that challenge our certainties. Why is it tilted on its side? Are the rings remnants of a shattered moon? How to explain this north polar cloud? These questions fuel debates and motivate the preparation of a large-scale mission. While waiting for a probe to arrive, space and ground telescopes are monitoring the inclined giant's evolution. The James Webb Space Telescope, combined with ground-based observatories, continues to feed the models. Each image of the rings, each clue of cloud variation, refines hypotheses and guides the design of the future mission. Neptune, the eighth planet in the solar system, has intrigued since its official discovery in the mid-19th century. Its existence was first predicted through calculations and then confirmed by observation. It was an achievement because showing that an invisible body influenced the trajectories of other planets opened a new era. Neptune was revealed as an extreme world, bathed in a blue glow and subjected to climates unknown elsewhere. Despite the distance, telescopes and probes have highlighted a dynamic atmosphere, traversed by winds of unmatched violence. These gusts, well beyond the speed of sound, show how the planet's internal energy and thermal contrasts generate spectacular phenomena. To understand what makes Neptune so special, its structure must be addressed. Located over 4 billion kilometers, or 2,585 million miles from the Sun, it harbors a core of rock and ice, surrounded by an envelope of fluids rich in water, methane, and ammonia. Its upper atmosphere consists of hydrogen, helium, and gaseous methane. This methane filters red light and gives the planet its bluish tint. These layers, subjected to colossal forces, host winds that can reach 2,000 kilometers or 1,643 miles per hour. When we talk about supersonic speeds, this is the kind of power we mean. A decisive moment in the study of Neptune came in 1989 when the Voyager 2 probe approached it within 50,000 kilometers, or 31,068 miles. It detected storms, including a massive one called the Great Dark Spot, comparable to that of Jupiter. This vortex already marked the intensity of Neptune's atmospheric phenomena. Since then, thanks to ground-based and space-based telescopes, astronomers have continued to follow these events, observing the birth, disappearance, or rapid movement of storms, sometimes in just a few months. This variability illustrates the complexity of air movements, even in a world so far from the Sun. The internal energy, a remnant of its formation, continuously fuels the atmosphere. Moreover, its rapid rotation strengthens the winds and the vortical cells. Among the most recent instruments, the James Webb Space Telescope, with its infrared capabilities, has reached a new level of observation. Its giant mirror and ultra-sensitive sensors render details more sharply and reveal the heat emitted from the lower layers of the atmosphere. In March 2025, this telescope succeeded in a feat, capturing an infrared aurora on Neptune. Auroras appear when energetic particles from the solar wind interact with the planet's magnetic field. channeling, collisions, and luminous emissions ensue. Here on Earth, these are the auroras borealis. At this distance, the solar wind is weakened, and Neptune's strongly tilted magnetic field complicates the task even more, hence the accomplishment of this capture. Seeing an aurora in infrared allows us to probe higher layers, track subtle chemical reactions, and analyze the solar energy absorbed. This also sheds light on the differences between giants like Neptune, Saturn, or Jupiter. Each detail enriches our understanding of planetary dynamics and opens up perspectives on distant atmospheres in the universe. In addition to this aurora, the year 2025 saw another significant moment. The Hubble Space Telescope observed a new dark storm named NDS 2023. This structure, visible for months, suddenly changed direction. It was heading towards the equator, then turned back toward the higher latitudes. This turnaround signals a deep shear phenomenon. This term refers to differences in speeds or directions in the atmosphere according to altitude or latitude. Winds, at various levels, pull storms in opposite directions. On Neptune, this absence of a solid surface makes the effect even more impressive as everything happens in fluid and mobile layers. NDS 2023 had already captivated researchers with its size and the presence of a bright cloud at its edge. This kind of formation is created when air rises, cools, and forms bright crystals. The rapid evolution of these phenomena allows us to test our models and measure Neptune's dynamics in real time. Each movement, each variation in intensity, reveals a part of its inner workings. The data provided by James Webb and Hubble is part of a broader exploration effort. Scientists hope that one day, a probe will approach Neptune and its moons, especially Triton, suspected of hiding an internal ocean. Better understanding Neptune's climate will facilitate the design of instruments on board, adapting them to the local turbulence and peculiarities. The information gathered on magnetic fields and air movements will feed future missions. For now, capturing the infrared aurora and tracking NDS 2023 are major milestones. The aurora shows how Neptune absorbs solar energy. The storm, with its strange turn, highlights the gaps in our understanding of planetary winds. These discoveries motivate research and pave the way for new models, which may perhaps be used to understand exoplanets with unstable and distant atmospheres. As we close this chapter on Neptune, we remain struck by the strength of the winds, the volatility of storms, and the responsiveness of the atmosphere. Even though it is distant, the planet shows overflowing activity. The auroras detected in infrared prove that the sun still influences its upper layers. The storms that change direction without warning remind us of how difficult it is to model the atmosphere of these giants. Each image, each measurement, brings us closer to a better understanding. Technology continues to progress, and future observations may one day tell us what lies behind the swirling mysteries of this fascinating planet. Imagine yourself in orbit around Neptune, more than 4 billion kilometers, or 2.5 billion miles from the Sun. You see a pale and icy sphere, Triton. Discovered in 1846, this moon is distinguished by a backward trajectory. Instead of following the rotation of its planet, it moves in the opposite direction. This strange behavior has long intrigued. Could it be a small world from the frozen fringes of the solar system? Today, thanks to observations from the James Webb Space Telescope, we discover that Triton holds many mysteries. active nitrogen geysers regularly project fine particles into space. These plumes form immense dark streaks carried by the solar wind. This discrete and fascinating spectacle reveals surprisingly recent geological activity for a world so distant and cold. Nitrogen, the main gas in Earth's atmosphere, freezes on Triton's surface, where temperatures hover around minus 230 degrees Celsius or minus 382 degrees Fahrenheit. Yet, the geysers show that internal heat allows this gas to gush out. How can a celestial body so distant, expected to be frozen to the core, emit such energy? Scientists suggest the idea of an ancient capture by Neptune, leading to intense gravitational forces. This phenomenon, called capture heat, would have generated internal friction sufficient to warm Triton's innards, thus releasing heat in its deep layers. The new images from James Webb add to those of Voyager 2, which flew by Triton in 1989. Even back then, the probe identified long dark streaks that were distinct from crater shadows. Today, James Webb's infrared instruments confirm that they are indeed nitrogen geysers. These eruptions occur when a slight solar warming is enough to melt a layer of ice, turning solid nitrogen into gas. This gas accumulates under the crust, breaks through the surface, and then escapes in spectacular sprays. Another remarkable aspect of Triton is the possible presence of a hidden ocean beneath its crust. Recent studies suggest a mixture of water and ammonia. This compound acts as an antifreeze, lowering the freezing point of water. Despite a frigid climate, such a mixture can remain liquid at depth. This ocean, concealed under 30 to 40 kilometers or 19 to 25 miles of ice, would extend over a large portion of Triton's interior. This type of ocean, termed global, would be kept liquid by the residual heat from the capture and the slow decay of radioactive elements in the mantle. The dynamics of the rocky and metallic core could also contribute to this heat. Once unthinkable, this hypothesis now aligns with those formulated for other icy moons in the solar system. With its retrograde orbit and nitrogen geysers, Triton may share much more with these oceanic worlds than previously thought. To confirm the presence of this ocean and assess the amount of ammonia, researchers model the data collected by James Webb and other telescopes. Infrared signatures reveal the composition of the ices, and sometimes even provide clues about what is happening in depth. Laboratory comparisons show that water mixed with ammonia produces precise spectral fingerprints when it reaches the surface, propelled by the geysers. The results agree. The recorded pressures and concentrations make a still liquid ocean possible today. This perspective fuels another question. Could Triton harbor conditions conducive to life? As soon as a world possesses liquid water, the possibility of organic chemistry is considered. Even if the crust seems to completely isolate the interior, occasional fractures could allow the passage of dissolved compounds. Water and ammonia create a complex chemical environment favorable to the formation of prebiotic structures. The absence of dedicated missions currently prevents any certainty, but the exploration of other similar moons makes this hypothesis increasingly plausible. The very existence of geysers suggests heat circulation in depth. Over time, the base of the crust is heated by the core. In places, the ice cracks. Gas pockets form, rise in pressure, and then break through the surface. James Webb has revealed streaks several hundred kilometers or miles long, signs of lasting eruptions. The activity is seasonal. Triton takes 175 years to complete an orbit. Each seasonal variation, however slight, is enough to restart the freezing and sublimation cycle. The capture heat deserves clarification. During its encounter with Neptune, Triton was likely an object from the Kuiper belt. Captured suddenly, it lost part of its kinetic energy in the form of internal heat. Then, for a time, it underwent extreme tidal forces. Internal friction generated persistent heat. Once the orbit stabilized, this heat slowly dissipated, but slowly enough to maintain a liquid reservoir mixing water and ammonia. This process would explain why Triton is still geologically active. It is therefore not just a frozen block of ice. It shows signs of activity: few craters, renewed regions, active plumes. Infrared images reveal warmer areas, likely associated with underground fractures. Every detail counts. The distribution of heat, the internal structure, and surface signs tell a complete story. Triton becomes a real laboratory for studying the evolution of icy bodies at the edges of the solar system. Several teams are dreaming today of a mission dedicated to Triton. An orbiter equipped with radars and chemical instruments could confirm the existence of the ocean and measure its composition. A surface probe would analyze deposits from the geysers. If the ocean occasionally communicates with the surface, traces of organic chemistry could be detected there. In the meantime, James Webb remains our best observation window. Its infrared readings already offer a stunning glimpse of the activity of this distant world. Here we are at the edge of the solar system, in a distant and icy region called the Kuiper belt. Located well beyond Neptune, this area is home to many objects that exist in constant cold, at temperatures close to minus 230 degrees Celsius or 382 degrees Fahrenheit. Among them, Pluto holds a special place. Long considered the last planet, its status has changed, but its importance remains intact. Not far from Pluto, other bodies intrigue us, like Arrokoth, which the New Horizons probe explored after flying over Pluto. To unravel their mysteries, researchers rely on advanced instruments and constantly revised models. In 2015, New Horizons revealed Pluto's landscape, dominated by a vast ice plain, Sputnik Planitia. Polygonal patterns and fine ridges are observed there. At first glance, such a cold world seemed incapable of harboring liquid water. However, recent research shows that a mixture of ammonia and salt could maintain an ocean beneath the ice. This type of ocean is described as eutectic. The substances present prevent the water from freezing even at very low temperatures. The latest models, published in 2025, indicate that internal heat, resulting from the decay of radioactive elements and protected by icy layers, could keep this ocean active. Enriched with ammonia and sodium chloride, it would be inhospitable to life as we know it, but its existence would open new perspectives. If such an ocean exists at this distance from the sun, other similar worlds could also harbor liquid water. Scientists analyze each image and each measurement to detect signs of tides and fractures, indicating this buried mass. After Pluto, New Horizons continued its journey towards Arrokoth, situated more than 6 billion kilometers or more than 3.7 billion miles away. This object, formed of two merged lobes, fascinates with its shape and color. During its passage in 2019, the probe revealed its composition and intense red hue. This color, more pronounced than on other bodies in the belt, could result from the action of cosmic rays on ancient organic compounds, altering their structure and hue. But Arrokoth holds other surprises. The onboard instruments detected sugars like ribose and glucose. These compounds, although they do not prove anything regarding life, indicate rich organic chemistry. Cosmic rays, interacting with ice and other molecules, can produce more complex structures. Thus, Arrokoth becomes a precious witness of the chemical past of the solar system, a sample preserved since the dawn of planets. Its structure, almost intact since its formation, also reveals a peaceful history. Its shape suggests a gentle merging of two blocks from the same original cloud. Understanding how they united without breaking allows us to reconstruct the early stages of planetary formation. Arrokoth is therefore much more than an icy rock. It is a vestige of origins. New Horizons mission does not end there. Researchers hope to find it a new target in the belt. Using telescopes like Subaru in Hawaii and Vera Rubin in Chile, they are looking for a target close to its trajectory. It is crucial to act before the probe runs out of energy or fuel. Finding a new object would enrich our knowledge of icy bodies and help us better understand the stages of planet formation. Beyond curiosity, the stakes are immense. Each flyby offers valuable data on the geology, surface activity, and chemistry of distant objects. Studying Pluto, Arrokoth, and potentially another unknown body will refine models, spot rare compounds, and contemplate the presence of underground waters. The Kuiper belt, long theoretical, becomes an active frontier where each discovery challenges our certainties about life and the formation of worlds. Beyond the known planets, far past Neptune, stretches an icy halo that astronomers call the Oort cloud. This vast reservoir is thought to contain billions of comets, formed from ice, frozen gases, dust, and rocky fragments. When a comet from this zone enters the solar system, the heat from the sun vaporizes its ice, creating a glowing coma accompanied by a long tail. The Oort cloud remains a hypothesis to this day, due to the lack of a probe having explored it directly, but evidence is growing, suggesting the existence of a massive spherical cloud at the edge of the solar system. The idea was proposed in the last century by Jan Hendrik Oort, who based it on the observation of so-called long-period comets, some taking hundreds of thousands of years to return. Their distribution and direction suggest a distant origin in a spherical zone well beyond the planets. Today, simulations and observations converge on the idea that a gigantic cometary reservoir is hidden tens of thousands of times the Earth-Sun distance, 1 AU Chishyaoks, about 93 million miles or 150 million kilometers. This reservoir remains stable until a disturbance caused by the passage of a star or the influence of a giant planet propels a comet toward the center of the solar system. In this context, Comet C 2023A3, also known as Tsuchinshan Atlas, is drawing attention. According to several forecasts, it could become one of the brightest seen in over a decade. In October 2024, it could reach a magnitude of 0.4, making it visible to the naked eye in a clear sky. The lower the magnitude figure, the more luminous the celestial body. Such a low magnitude suggests the potential for a remarkable spectacle, provided that the comet maintains its trajectory and its activity does not diminish. The key moment will be around January 12, 2025, when it comes closest to the Sun, at the point named perihelion. It is at this moment that its internal ice releases the most gases and dust, feeding a spectacular coma. Its actual brightness will depend on several factors: core size, ice amount, viewing angle, but the potential is great. If conditions are right, it will be a rare celestial event. But beyond the beauty, the scientific interest is immense. Comets are witnesses to the past, preserving the materials that compose the early solar system. They offer clues about the nature of the initial elements, the formation of water, and the distribution of organic molecules to the rocky planets. Each cometary passage is an opportunity to study the composition of the gases they emit. These analyses reveal essential details about the origins of the elements present on Earth. A study planned for 2025 will specifically focus on the isotopes of water in comets from the Oort cloud. Isotopes are versions of the same element that vary in mass. For water, the comparison is between standard hydrogen and the heavier deuterium. This ratio, noted D/H, varies among comets. This diversity is valuable. It helps trace the paths by which water could have reached Earth. Variations measured among different comets suggest there was not just one water reservoir but several, formed under varied conditions. These results challenge established models. It appears that the water contained in comets did not originate from a single place or time. Variable proportions of deuterium indicate that the ice formed in diverse environments before being dispersed through the disk of matter that surrounded the young sun. These comets could thus reveal a much more complex history than expected, and perhaps even rewrite the origins of Earth's water. Some theories suggest that Earth received part of its oceans through impacts from comets or asteroids containing ice. But the question remains, did these contributions come primarily from Oort cloud comets, objects in the asteroid belt, or so-called Jupiter-type comets? Researchers rely on precise observations to decide. High-resolution ground-based telescopes, as well as the James Webb, will be mobilized to analyze the light emitted during ice vaporization and thus determine the isotopic composition. The analysis of the infrared signature of the released water will allow for the precise calculation of the deuterium to hydrogen ratio. Each cometary passage becomes an opportunity to validate or invalidate existing theories. In 2024 and 2025, Comet Tsuchinshan Atlas and parallel isotope research will mark a turning point. If the new values deviate from the previous ones, it will be necessary to reassess the history of the solar system's ices. The big question will be to understand how these observations compare to those of other comet families. It will take several cometary passages from various regions to paint a global picture. Each measurement will add a piece to the puzzle of the origin of planets and life. Studying these ephemeral objects allows access to the secrets of the early solar system, and perhaps to those of conditions conducive to life. The Oort cloud thus becomes a key area for astrophysics. The slightest bright comet becomes a natural laboratory. It fascinates the public as much as it fuels research. In 2024, eyes will turn to the skies, waiting for the appearance of Tsuchinshan Atlas. In parallel, observatories will analyze each gas emission, each brightness variation, to extract precious clues. These studies will have a profound impact on our understanding of the origin of water and the emergence of life. They remind us that even at the solar system's frontier, icy bodies hold ancient messages. Sometimes, an ephemeral celestial event becomes the starting point for a rewriting of our cosmic history. If Tsuchinshan Atlas lives up to its promises, it will be much more than a bright spot in the night. It will be a messenger from a distant past, bearing essential answers to our quest for origins. At the dawn of the 2025 and 2035 decade, solar system exploration enters a new era. Imagine a near future where several probes launch toward still unexplored worlds, while ground and space observatories unite their efforts to unravel the mysteries of icy moons, metallic asteroids, or distant regions of our cosmic neighborhood. In this sequence, we will follow the major announced missions, the emerging technical collaborations, and the significant questions that animate current research. Each mission becomes a piece of the grand puzzle, helping to better understand the origin of our solar system. Among the major projects is the Psyche mission, expected by 2029. It targets an asteroid of the same name located between Mars and Jupiter, supposedly rich in metals such as iron and nickel. Unlike typical rocky bodies, Psyche could be the exposed core of a planetary embryo whose outer layers have been stripped away. Studying its structure will help us understand how planets have formed and differentiated. The instruments on board, such as spectrometers and magnetic field sensors, will analyze the distribution of metals and the internal composition of the asteroid. These data will provide valuable insights into the stages that shape the Earth and other planets. Another crucial mission, Hera. It will return to the Didymos double system, composed of a large asteroid and its small satellite Dimorphos. A previous probe had collided with Dimorphos to test the deflection of a celestial object. Hera will analyze the effects of this impact, measure the orbit's evolution, and examine the debris. This return will refine planetary defense strategies while enriching our knowledge of these bodies' internal structures. Understanding how to deflect an asteroid is not just a technological feat, it's also a global security imperative. On the icy moon's front, two missions are anticipated: Europa Clipper, en route to the moon Europa, and Orbilander, destined for Enceladus. These two moons, situated around Jupiter and Saturn, are believed to hide under their frozen surface a liquid water ocean maintained by internal forces. The gravitational pull of the giant planets regularly deforms the interior of these moons, producing enough heat to keep the water in a liquid state. Occasionally, plumes of water vapor escape from the crust. Europa Clipper will fly over Europa to map its surface and analyze these emissions. Orbilander will go further. It will orbit Enceladus, and then attempt a landing to study the jets and the composition of this fascinating moon. Another ambitious mission, called Dragonfly, is preparing to launch to Triton, the largest moon of Saturn. If all goes as planned, it will arrive by the end of the decade and deploy a flying craft capable of surveying the surface. Triton has a dense atmosphere and seas of liquid methane. Its complex chemistry makes it an ideal ground for astrobiology. Dragonfly will study sediments, dunes, and atmospheric molecules, searching for mechanisms that could have given rise to primitive forms of life. Another project in preparation, a mission to Uranus. This tilted giant has only been closely observed once. Its internal structure, the dynamics of its rings, and the nature of its winds remain little known. An orbital mission around Uranus, coupled with an atmospheric probe, would allow us to probe its deep layers, analyze its composition, and measure its magnetic field. This type of planet, found in other stellar systems, remains poorly understood. By studying Uranus, we could expand our knowledge of icy worlds and better understand their formation. Alongside these probes, powerful telescopes will enhance observational capabilities. James Webb, already operational, the Nancy Grace Roman Telescope, in preparation, and the Vera Rubin Observatory. Each brings complementary expertise. James Webb analyzes atmospheres and infrared signatures, Nancy Grace Roman will spot transient phenomena and exoplanets, and Vera Rubin will regularly scan the entire night sky for rapid changes. By combining their observations, it will be possible to obtain a detailed picture of activity throughout the solar system. For example, if Vera Rubin detects a distant comet, James Webb can observe its composition, while Nancy Grace Roman will track its evolution. This synergy offers unprecedented prospects for studying icy objects and unexpected celestial events. The union of these tools paves the way for faster, more connected, and more precise science. Meanwhile, innovative concepts are emerging, such as solar sail probes. These ultralight devices would be propelled only by light. Photons emitted by the sun would exert a continuous thrust, allowing navigation over long distances without fuel. Small probes equipped with miniaturized sensors could reach the Kuiper belt or even beyond at low cost. Real-world condition tests are planned in the coming years. With these projects, big questions emerge. How long have icy moons harbored water? How did this water form, and in what form does it exist today? Will Saturn's rings disappear in the near future? What is the stability of these structures over time? Finally, could some moons harbor life? Europa, Enceladus, Triton, so many worlds where water, organic molecules, and energy sources are found. The next missions will seek to detect the traces of possible life, even microscopic. The period 2025 to 2035 promises to be a golden age for exploration. From asteroids to icy moons, distant giants to the edges of the Kuiper belt, each mission promises a decisive advance. The diversity of techniques and cooperation between agencies and observatories build a richer and more precise picture of our celestial neighborhood. Each step brings us closer to a global vision. The solar system appears as a collection of contrasting worlds shaped by various forces, each carrying clues about the history of life and planets. Perhaps we will soon discover that Earth is not the only oasis in the cosmos. What matters is the rigor, curiosity, and collective drive that push us to explore. Because the true journey is not just the distance traveled, but the knowledge we gain from it.